Okay, we're going to continue on here lecturing. We got into chapter 2 last time, and essentially a lot of what we talked about had to do with measurements and how to properly take measurements, which you'll get a more experience later today. Remember, as we talked about, whenever we do take measurements, there's always some degree of uncertainty in that measurement. And you always want to look at the scale that you got going on there. So as we saw last time when we looked at a scale such as this, like a ruler, you really want to look at the large markings there. And in this particular case, our large marking being 1 centimeter. We also want to figure out how many of the small markings there are between each of the larger markings. Remember that when we start counting, we really do start counting past the first large marking, and we go until we hit the next large marking, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 in this case. Since there's 10 of the smaller markings, each of those smaller markings, as we saw, was, bless you, basically 0.1 centimeter. We can figure out, again, sort of the tolerance of our equipment by taking the smallest markings and dividing it by 2, which in this case would give us 0.05 centimeters plus or minus. And again, that is essentially how far you should take this reading to. So if we were going to measure a line like we looked at before, there is 1.1, 1.2, 1.3, 1.4, 1.5. There are certain numbers, as we talked about, that everybody should agree upon. And in this case, something like 1.5, they would agree upon. The last one there is that estimated digit. And again, you're sort of to imagine in between those markings, nice even distribution of everything. And you may look at it and go, I think it's like dead on center, or maybe it's not. And you may record A5, which is sometimes referred to as the first uncertain digit, the estimated digit. And that's really where our uncertainty comes into play here. And that would be centimeters plus or minus 0.05 centimeters in this case. This is really, as we talked about, when you record those first uncertain number and all the certain numbers. Those are, again, our significant figures. And this guy does have 3 significant figures in this particular case. We also talked about, again, if you do sort of get right on a marking or something like that, you do have to preserve sort of the tolerance or how far you can take the reading by adding a 0. So again, if we were measuring something like this and it was dead on this 1.5 marking, you do need to record it as 1.5 centimeters, 1.50 centimeters. With that 0 there, preserving it to the third significant figure, which is how far we can take the reading. As we talked about last time, if you sort of leave off that last 0, you have something that's 2 significant figures and a lot worse of a measurement than the other one. With that, we did talk about significant figures. And remember that pretty much all non-zeros are significant. So any number that is a non-zero will be significant. We always start counting left to right there with our very first non-zero as our first significant figure. So something like that would have 3 significant figures. We do have leading zeros, and those are not significant. So you could have as many zeros as you want leading into that first non-zero number. None of those are significant because we would not start counting until we hit the 8. Then we would have 3 significant figures, obviously, at that case. And then the zeros at the end, which are sometimes, actually, we have captive zeros. Yeah, I spelled that right, not cat, captive. There you go. Captive zeros or trap zeros, those are significant. So those would be the zeros that find themselves between 2 non-zero numbers. So in that case, that guy would have 5 significant figures. It is those trailing zeros at the end which may not be significant or it may be significant, and it is that decimal point. So if there's a decimal point, thank you. If there's a decimal point anywhere in that number, then that makes all those zeros at the end significant. A reminder, it does not have to be near those zeros. So if you got something like this, not significant, 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 and these are significant because of that decimal point that's in that number. So any questions on that there? Okay. All right. So continuing on with sort of our significant figures conversation and just calculations in general. Rounding. So normal rounding rules obviously do apply. So if wherever you need to lay it up to round a number, if the next number is basically kind of 4 or less, you basically just drop those numbers. If wherever you need to round the next number over is greater 5 or greater, we do round up by 1. It's important, again, not to do super extreme rounding, which very often, again, happens to a lot of people because they're focusing so hard on giving the right significant figures and answers and all that, that they sort of overdo it. So for example, here, if I wanted to give this to 2 significant figures, the correct answer here is 13,000, right? It is not 13, although 13 and 13,000 both have, the way I wrote it, 2 significant figures. There is a very, very big difference, right, between the meaning of 13,333 and 13, right? That's basically not the same number, even though it has the right number of sig figs you're looking for, bless you. 13,000, on the other hand, is pretty much the same number as 13,333. So you never, ever want to go overboard on the rounding, which, like I said, is a very common thing that people do, especially on these early chapters, because of like, I want to make sure for sure sig figs, that you ever change the meaning of the value. So obviously in this case, 13,000 would be the correct way to do it. You also could, as we talked about, use something like scientific notation to accomplish the same thing. This would have 2 significant figures written like that. As we talked about, any number that's written in scientific notation, all of the numbers that come before the times 10 part are significant. So you could actually really control your significant figures with scientific notation. And as I might have mentioned last time, in certain cases, it is really the only way you can maybe report the answer to the correct number of significant figures. So if I needed 4 significant figures in this case or something like that, I could do something like this. And now I have 4 significant figures. So scientific notation is a good way to sort of control how many significant figures. And again, sometimes it's the only way to do it. Any questions on rounding? Yeah. Other really important things about rounding is if you do a bunch of sort of calculations together, and what I mean by that is maybe you're going to do a calculation, get an answer, take that answer and then do another calculation with it, get an answer, take it and do another sort of math step with it. It's really important to not round really until the very end. So you really should hold off on rounding until you get to the very end. If you round sort of after each individual sort of calculation that you do, you actually will move yourself kind of further and further away from the correct answer. But it's important to keep track of, you know, where you should end up as you're doing the steps in the calculation, which we'll talk about in just a second. So sometimes what people will do is they'll keep a couple extra digits, sometimes referred to as a guard digit, and kind of keep a few extra digits as you go through the calculation. Personally, me, I will probably write down a few extra digits sometimes, as if I do write down a number, am I going to continue on the calculation? Personally, I will keep the whole number usually in my calculator and just kind of continue on with whatever my calculator gives me, and then sort of clean it up at the end. They mostly want you at the school in chemistry here to do everything in sort of one big calculation, but I personally don't care if you kind of break it up into individual ones. But if you choose to do that, just make sure you don't kind of round to the very end. Otherwise, you may find yourself sort of off in terms of the answer. Any questions on that? All right, so obviously here, if we're shooting for two significant figures, we're going to go to here, which would be our second significant figure. We would look at the 7 and round up, and we will end with 36. Here, looking at two significant figures would move us to the 8 in this case. We would look at the 2, which means we're just going to drop the rest of them and do something like 3,800 grams. Would I put a decimal point at the end? I would not in this case, because then I would have 4 significant figures, right? So I don't want to add a decimal point if I don't need it. We also obviously could do a little scientific notation on any of these. Here, none of these count until we get to here. That means that the 6 here is, again, our second significant figure, and that would get us 0.0026 liters. And lastly, here, our second significant figure at that 2. We look at the 8, which means 1.3 kilograms is what we should shoot with here. Any questions on any of those there? Also, a reminder as well, again, your calculator does not always give you the answer, obviously, to the correct number of digits and stuff like that. So you do have to round appropriately, especially when you take answers from your calculator. So more importantly, obviously, as well, in addition to writing or figuring out significant figures and numbers, is to figure out in calculations how many significant figures you should end up with. So there's really kind of 2 sets of operations or math operations that we typically do. We typically either multiply and divide, or we sort of add and subtract. So there are different rules that we follow specifically based on what we're doing. If we are multiplying or dividing, we are actually looking at significant figures. So we're going to look at all the numbers we're multiplying or dividing, and the answer should have the same number of significant figures as the one with the least number of significant figures. So we're looking for sig figs. Whichever number is the least number of significant figures is what our answer should have. So if we took something like 4.0 and we multiplied it by 323, we are multiplying, that has 2 significant figures. This has 3 significant figures, which means, again, here our answer should have, I'll learn to count, 2 significant figures there when we're done. So if we did that math there of 323 times 4 on our calculator, we will end up with 1292. 2 significant figures goes to here because of the 9. Our answer should be something like 1,300 in this case, which again would have 2 significant figures. Now, when we add and subtract, it is a little bit different in terms of what we're looking at. We are not looking at significant figures here when we add and subtract. We are actually looking at decimal places. So your answer should have the same number of decimal places excuse me, as the number with the least number of decimal places. So if we were going to do some adding here, 1.112, 3.2, 4.04. I'm going to try it without the calculator. Give it the old college try. That's going to be like a 5. Maybe that's a 3. Maybe that's like an 8, something like that, hopefully. So in this particular case, we're not looking at significant figures when we're adding. We are looking at decimal places. And in this particular case, this has 3 decimal places. That has 2, and that has 2. That has 2. The top one has 3. And the middle one has 1. So we are going to look at the 1 decimal place here. We will take our 5 and we're going to round up, and we should end up with 8.4 in this particular case. 8.4 has 1 decimal place, but it has how many significant figures? 2, which would be important if you're going to then take that number, maybe do some multiplication or division. This would happen in that particular case. So it's important to keep track of what is happening, and usually kind of like the last step that you did. So if you were going to do multiple things together, maybe you're multiplying and adding, or dividing, multiplying, doing all these different steps together, you want to keep track of your significant figures and where you should end up. And it's really usually that last sort of math step that you do that will determine sort of where you will end up in it. So if I were to sort of combo a bunch of things together, take like 325 times 1.2 divided by 4,635. In this case, typically speaking, we do the part in the parentheses first. So we would be multiplying here. And that is 3 significant figures. That is 2 significant figures, which means technically speaking, when we do the top part of the calculation, we should have 2 significant figures. The next thing that we would do, right, would be take the top number and divide it by the bottom. So since we're dividing, we are still looking at significant figures. We would take 2 significant figures divided by 4, which means our answers should end up at 2 significant figures in this particular case. So if you punch this into your calculator, 325 times 1.2, I would hit equals. It actually worked out okay in this case, but you actually would end up with something that is 390, which actually is 2 significant figures by luck. But in case you didn't end up with something that was 2 significant figures, I would take it to a digit or 2 past where you should end up. I wouldn't round very much at this point, and I would use really the whole thing in the calculator. Question? Yeah. You wouldn't round up in that on the case on the right there. If it happened to, if the smallest was 2, you would end at 8.35. Yeah. So in this case, we would then divide by 4,635, and we will end up with on our calculator something like 0.084142395. Now, when we talk about keeping digits, that's probably like way too many digits as you need to keep, right? So you should never give an answer that far. But in this case, we should end up at 2, which would be here. 0.084 would be the right one. So personally, I don't really round very much along the way, but I do keep track of what's going on until we kind of get to the end and do sort of the final step. Now, a couple of things on that. Let's just say at the end of this, you were going to add it to like 3.2 or something like that. At this point, we would still kind of keep track of everything we did on the front part. I know that we would add the 0.084 to the 3.2, and we'll end up with something like probably 3.284142. 395 if we did that. At this point, right, I should end up with, should I be looking at significant figures at this point, or should I be looking at decimal places? I should be looking at decimal places, right? The last thing I did was add. So at this point, if we were to add this to the problem, I know that I should really end here, right? Which is actually 3 decimal places, right? And I should end here with 1 decimal place, which means I should actually end with 1 decimal place when it's all said and done over here. So again, if you had that additional operation that you're going to do at the end, you want to think about after you do all your multiplying and dividing on the front part, where you should end up. And then now we need to switch over to looking at decimal places and end up with the right decimal place. Lastly, if I were to add all these numbers together that we did originally, and let's just say that this was like a 3, not 3.2, but just 3 whole number, I should then take the answer to a whole number. Yeah. So if you have a whole number that you're adding, and there is no decimal place, then you should take your answer to a whole number. The purpose behind the take the least number of sig figs, the least number of decimal places is it is frankly your worst sort of measurement, if you will, right? So the other day we talked about your sort of measurement and all that, your calculations, it's only as good as your weakest measurement. And that's why we take the least of each of these. So if we were going to a whole number in that was kind of our crappiest measurement, right? So the best we could do in our calculation is to say it's as good as our worst measurement. So kind of as good as your weakest link. Yeah. Yeah. In that particular example earlier that we were looking at where we had 13,333, And if we were still going for two significant figures, if that's your question, because the second significant figure would be here, we would then need to look at that to decide, what we should do. Should we just drop the numbers? And in this case, we can't really just completely drop the numbers because then it actually changes the meaning of it. So we have to drop the numbers in that sense by putting zeros in there, so it maintains really the value of it. But we did end up with the right number of significant figures, because when we then turn this into 13,000, although it maintains the 13,000, the value of it in terms of significant figure wise, those are not significant zeros in this case because there's no decimal. Well, it's really determined when you go to round. It's really based on the sig figs and sort of where you need to end up in terms of the answer. So unless you had a question like, here's a number and just give me that number to 3 significant figures, So other than that, in most cases, how you're going to come across it is you're going to be doing a calculation, right? And so it's going to be based on the calculation you're doing as to how many, say, significant figures you should be looking at, or how many decimal places you should be looking at. And whichever that answer is, once you figure out where you should go, then you always need to look to the guy to the right of it to determine, rounding wise, should you just kind of get rid of them or round up. Other questions? All right, so let's take a look at some of these here to kind of see what we end up with. We got 6.25 times 1.5 gives us on our calculator 9.378. A reminder again, it will not give it to you in the right sig figs or anything like that, your calculator. So we are multiplying here. So that is 3 significant figures. That is 2 significant figures. That means our answers should end up at 2 significant figures. And that means that we should end up here. So in this particular case, because of the math operation, we want to then look at the 7. And we do need to round up, which would give us 9.4 in this particular case. Yeah. Looking at the next one, we're dividing. So we're looking at sig fig. So that guy's got 4 significant figures. That guy's got 3 significant figures. So we're going to look at 3 significant figures, which actually puts us to the 8, as those zeros at the front are not significant. And we would look next door, and that is a 2. Now, in this particular case, we can just drop the numbers, and we will end up at 0.0758. Why would we not want to turn those guys at the end into just zeros? Because then it would have the wrong number of significant figures. So although we'll still have the same value in this particular case, because this does have a decimal point in the number, if you add those zeros at the end, you're implying that they are significant, and it would be the wrong number of significant figures. Yeah. So here we are adding, which means we do want to look at the number of decimal places. So that's a couple decimal places. That's 1 decimal place. That is 3 decimal places. So the smallest number of decimal places is 1. So once again, here we are going to just drop those last numbers, and that's going to be 29.1. And lastly, here we're subtracting. So 4 decimal places and 1 means we should end up at 1 decimal place and a 0.6 happening here. Yeah. Any questions on significant figures and calculations? Again, my recommendation is to keep track of what you're doing along the way, not really round, and then sort of clean everything up to the proper number of digits at the end. And that usually will give you sort of the right answer. And especially important not to round too much if you're doing multiple steps and getting answers along the way. Any questions? And again, like I said, sometimes people keep guard digits. Sometimes you'll see people write numbers and they'll put like a little line over it to like, hey, that's where I really should be stopping my sig figs or something like that. If you want to do that, you can. You don't have to. But people sometimes will do that. So if you see a little line over some people's numbers, that's sort of what they use as like a guard digit. Like technically that's where I should stop, but I took a couple extra digits past there to continue on my calculation. Any questions? Okay. So let's talk a little bit more about some of these conversions. We talked about metric units and prefixes, and I think we might touch upon some of these, but just a reminder that for the most part, you will come across most of these sort of prefixes in chemistry. For our class, you probably will come across kilo a lot, centi, milli, and maybe nano. But as you continue on to 1A, for sure, the probably micro and mega will pop in as well. So a reminder that when we use these prefixes, you want to make sure that you do use them correctly. So something like deci is 10 to the minus 1, and that really is 1 times 10 to the minus 1 if you need to put it in your calculator that way. And what that represents, for example, is if I have a decimeter and a meter in one of the prefix unit, which in this case would be decimeter, that would give me 10 to the minus 1 meters, which is the base unit. So the base unit in this case is meters, right? Decimeters and meters. The base unit there basically is meters. It really doesn't matter, right? When you look at something like this, if you had nano, which is 10 to the minus 9, in 1 nanometer, which is the prefix unit, there is 10 to the minus 9 meters. And that is the proper way to do that. Most people will always reverse it, and do it wrong. Do something like 10 to the minus 9 nanometers is 1 meter. But again, it is when you see the 10 to the 3, all these guys, that is how much there is in the base unit to one of the prefix units. It doesn't matter really what the base unit is. If I had 1 nanoliter, that would still be 10 to the minus 9 liters, right? So it works the same way. It doesn't really matter if it's liters, grams, it's the base unit. If I had 1 nanogram, that is 10 to the minus 9 grams. So it works the same way, regardless of which one did you have. Same thing with centi, for example. If I have 1 centimeter, that is 10 to the minus 2 meters. And again, sometimes you'll even see the larger versions of these conversions, and we get that by dividing 10 to the minus 2 to both sides. Gives us 100 centimeters is 1 meter, right? So both of these conversions are exactly the same. You can use them both ways, but you definitely want to make sure that you use it correctly. And it's a super common mistake that people always kind of run to do backward. So you should probably be familiar with this table. You should have this table probably in your book as well. And these are very common prefixes that we come across a lot. Any questions? Hold on there. All right, so we touched upon these earlier, but just to review some of the important ones. Yeah, pretty much everybody on this page. Yeah, so we have 100 centimeters is 1 meter, 1,000 millimeters in a meter. And as we talked about when we look at a ruler, right, there's 10 smaller markings on the bottom for every 1 centimeter. So 10 millimeters in a centimeter. This is, I would say on this page, this is one that you definitely should know for sure. We use it a lot in chemistry. 1 liter is 1,000 milliliters. Also, our 1 milliliter is the same as a cubic centimeter, right? And that is also a relationship that we see a lot with volume. Reminder that the cubic centimeter, also sometimes referred to as the cc, which is a cubic centimeter, it's the same as a milliliter. This is sort of one way that we could get a volume of something by taking the length times the width times the height, like you'll do today with the ruler for a cube. And again, if each of these were measured in, say, centimeters, and we multiply them together, that is how we get our cubic centimeters, which once again is a volume. Each of these individual measurements are actually length measurements, right? So whenever you take any type of length measurement and you cube it, it basically becomes a volume. And obviously that's our graduated cylinder. So getting the volume measurement through length times width times height is one way. Clearly, as we also talked about the other day, you can use something like a graduated cylinder, which is what we're looking at here. And that's a really good piece of equipment to measure out the volume of a liquid. And we always, as we talked about, want to make sure that when we are looking at a volume, we try to find the meniscus, right, which is that curvature of the liquid. And we always read from the bottom, right, of the meniscus in most cases, especially when the meniscus looks like a U. That is how you do it. You kind of read from the bottom. In terms of mass, I would say definitely for our class, these couple conversions, again, we do see a lot, and that's our 1 kilogram is 1,000 grams. Our 1 gram is 8,000 milligrams. All right, we'll skip some of those there, I think. So let's talk a little bit about writing conversion factors, which is really important. And this is leading into, as we talked about, sort of really how they want you to do problems and show your work in chemistry here as you go through their different chemistry classes. And it's really using conversion factors, and it's also using dimensional analysis, which is a way that we set up these problems that uses really units and conversion factors to allow us to go from one unit we're not really interested in to another unit that we are interested in. So a conversion factor really is nothing more than a fraction that we could use in this process. And you can write 2 conversion factors from anything that is known as an equality. So when we talk about an equality, something like in 1 foot, there is 12 inches. That's an equality. It basically is 2 different measurements that represent the same amount of something. So it's very much like if you had $1 and you had 100 pennies, that is the same amount of money. Just one's a penny, and obviously one's in dollar bills. You could go through the drive-through, right, and pay either way, right? Although they may not let you through the drive-through if you keep showing up with all your spare change, like this is how I'm paying. But it's all money, and it works the same way. So you can write for this particular equality 2 conversion factors. So for example, here we could write 1 foot on top and 12 inches on the bottom, or we could flip it around and go 12 inches is 1 foot. These are what are referred to as conversion factors. We do not use both conversion factors usually in a problem. Otherwise, you kind of undid the calculation. But we do use the one that we are needed or need to use to do it. So for example, if I had 42 feet and I want to know, how many inches that is, the way that they want you to show your work is like this, which is what is referred to as dimensional analysis. You would start with your 42 feet, although it is not written as a fraction. It's like assumed to be like over 1. That essentially means in terms of the units here, feet are on top. So one thing about math, right, is basically opposites cancel each other, right? Opposites do cancel each other out. So since we want to get rid of feet, we want to actually put feet on the bottom. And the conversion factor that will do that for us is this guy right here. So we would set it up like so, where we see our 1 foot on the bottom and our 12 inches up on top. What's going to happen here is we're basically going to multiply whatever's on top. We're going to come back through here and divide by whatever's on the bottom. When we do that, we are essentially dividing feet on top divided by feet on the bottom. They essentially cancel each other out. That's the same thing if I took 2 divided by 2, that equals 1, right? They cancel each other out. So if you have the same unit on top as you do on the bottom, they will cancel each other out. And you always want to put them opposites of each other. At this point, what is left is to really multiply. So we're going to take 42 times 12, and that's going to give us like 504. We're going to divide it by 1, which will still give us 504 inches. Are the only units that are left. So this is the way that you should set it up, all your work, showing the units, showing the conversion factors, showing everybody canceling. We do have to look at significant figures here. So we essentially multiplied and divided, which means we should be looking at significant figures. This is what is considered an exact number. So if you remember, our exact numbers are things that are either counted or definitions. So if I had these 3 pens here, right, I would just count them, and that would be considered an exact number. If I have some type of definition, a definition that is a English to English conversion, a metric to metric conversion, they are considered exact numbers. And what that means is when you're doing a calculation like this, you really don't have to worry about the significant figures of that because it could have as many as you want, really. So what that means, really the only number in this calculation that we should be concerned with in terms of significant figures was our original number. And our original number had how many significant figures? This number has 2 significant figures. That means that our answer here really should have 2, which means we have something like 500 inches. Is the way I wrote it 2 significant figures? No, it's 1. If I put a decimal at the end, it is 3. If I drop off the last 0 and put a decimal, it's 2, but it's now 50, right? Which is a different number. So this is a case where really the only way to get it properly would be a little scientific notation action. Yeah. Something like that now has 2 significant figures, and it still maintains as 500, so it maintains its value. So again, this would be an example where sometimes it does happen like that, that the only way to get it to the proper number of digits is to write in scientific notation. Any questions on that? I will say in dimensional analysis, if you're really doing a lot of conversions and really more so just doing a conversion problem, I won't say 100% of the time, but more times than not, your original number that you're converting is probably the right amount of significant figures, are pretty darn close to where it should be, but it's not 100%. So, but more times than not, a lot of times what's in the middle of conversions are exact numbers. So you kind of ignore those. So a lot of times you do default to kind of like that first number. And it usually is pretty close to the right sig figs, if not the right sig figs that you should have. Any questions on that? So obviously that's what we were talking about, our pennies and our 100 pennies here. So let's take a look at some common equalities. And as we talked about before, there's the English units, which is the US units. There's the metric units, and then there's really metric to US. So you should know some of these things, guys, here on this table for sure. I would say, again, this is used a lot. Hopefully you know that one, I hope. I would also say that maybe some quarts and gallons pop up a good amount. But if you're doing any type of conversion problem where you're using any of those equalities as a conversion factor, they will be considered exact numbers, so you don't have to worry about it. This is metric, which, as we've been talking about, pretty much you should know what's in this column for sure. And if you're using any of these equalities here, it is a metric to metric conversion, which means it is an exact number and you don't have to worry about it in your calculation. Now, if you come over to this here where we're crossing over, you actually do need to kind of take into account the significant figures in those conversion factors. There are a couple that you don't. This first one here is an exact conversion. So 1 inch is 2.54 centimeters, so you don't have to worry about it there. I would say a lot of books will actually use this conversion, but here at Saddleback, they would like you to know that there is 453.6 grams and 1 pound, and we will use that one here, and that's an exact conversion as well. Technically speaking, if you use the 454, it's not an exact conversion, and you should look at the significant figures. So let's just say we grabbed one like this guy here, and we were going to use it in a problem as a conversion factor. Let's just say we had it as like 1.06 quarts is 1 liter. If we had this somewhere in our sort of calculation part, we would want to look at the significant figures, and the number that we would want to look at is this number here, which we would count as 3 significant figures. A lot of times in this case, you'll have a number that's like 1, either on top or bottom. That's obviously not the one you want to look at. You want to look at the one that is greater than 1 in terms of the number, as usually are that is not 1 in terms of that. So we would count that. But even in a lot of cases, again, it's very common that, you know, your kind of smallest significant figure is kind of the starting number, but not in all cases. Any questions on that? You clearly should know time, I hope, right? So we got 60 seconds in a minute, right? 60 minutes in an hour, and only 24 hours in a day, not 60. Yes. You can tell me how many people put 60 hours in a day on a test, you know? I think they go 60, 60, 60. Seems like good. That seems like way too much. All right. So looking at conversion factors and write them again from any equality, you can write 2. So 5,280 feet in a mile. Gives us two conversion factors, 5,280 feet over a mile, or a mile is 5,280 feet. Once again, if we wanted to know how many feet there are in 32.5 miles, we want to set it up this way, 32.5 miles. Once again, not written as a fraction, but the miles are considered to be on top. So we want to go opposite to cancel. So we're going to grab that as our conversion factor. We're going to set it up as the mile on the bottom, the 5,280 feet up on top. The miles will cancel. And again, we're going to multiply whatever's on top, come back and divide by what's on the bottom, which in this case, there's not much to divide by since it's 32.5 times 5,280. Going to give us 171,600 feet. Now, in terms of significant figures, this is going to be considered an exact number, so we don't have to worry about it. That means we really should default back to this number here at the beginning, which has 3 significant figures. That means that our answer should end up here. That also means we should look at the 6, and we actually should round up in this case. And we would end up with something like 17200, I think. I think I lost a 0 there, one more maybe for good measure. And feet. Yeah. So that would have our 3 significant figures. Any questions on that one there? All right, some other conversions. Sometimes we are given things in words, like we're driving 65 miles per hour. Whenever you have something in words that is something per something, that basically, right? So that basically means you could go 65 miles in 1 hour, or you can go in 1 hour 65 miles, which would be your 2 conversion factors that you could get. Now, sometimes in dimensional analysis or conversion problems, you have units, 2 sets of units, and maybe you want to convert both of them to different units, right? So maybe you got like miles per hour, and maybe you want to end up at like kilometers per second, right? So you basically got to keep everything sort of straightened out. So if we were going to do some type of dimensional analysis approach, just looking at the units, we'd maybe try to find a conversion that would take us from miles to kilometers, right? That way the miles would cancel out first. If I stop right here on this calculation, the units I have are kilometers per hour, right? And it's important to set it up like this in dimensional analysis, because now I could clearly see that the hours are actually on the bottom, which means to get rid of hours, I need to put them on top, right? And again, I can't tell you how many people will do it, not in dimensional analysis, which is what you're supposed to do, but they really have no idea, you know, should I be like dividing by that number? Should I be multiplying by that number? So setting it up like this allows you to really visually see, okay, I should be multiplying or dividing by these numbers. So again, there's multiple ways, by the way, to do conversions. You could, you know, figure out the hours to seconds conversion, right? Like 3,600 seconds in an hour or something like that. You could also, if you wanted to, at that point, the hours would cancel, and that would give us kilometers per second. You could have as well took it step by step as well and did your kilometers and miles conversion. You could have then did, okay, an hour to minutes, a minute to seconds, and all those would cancel out as well, right? And leave you with kilometers per second. So there are multiple ways, depending on what pathway you choose, what conversion factors you choose to do, you can potentially do a conversion different way and end up with the same answer. It's all good as long as you choose something that's a legit conversion, not one you made up yourself, right? So as long as you choose something that is a real one, you can actually do the same problem different ways depending on which way you chose. Any questions on that? So the way these are being set up here is what's known as dimensional analysis, and that is the way they want you to show your work here in chemistry. And it really does benefit you because, like I said, it's very common, especially when you got 2 units and time involved. I've seen many exams where people, again, multiply when they should have divided and divided when they should have multiplied. So it just allows you to visually see that. And again, when you're doing in terms of the math is multiplying anything that's on top and coming back through and dividing by everybody that's on the bottom. If we had a gallon of gas, that's 91 octane is 305. Did I say 305? This is 305. By the way, that was expensive when I made this. That's how old I am. Yeah. I think we would all love 305 right about now. All right. But basically, that means 1 gallon would be 305. Our $300.05 would get you a gallon of gas. Also, a really common thing that we come across a lot in chemistry is percentages. So we do come across a lot of percentages, and a lot of times we do want to convert our percentages into kind of a usable sort of conversion factor. So as you may be familiar with, right, if you do have a percent, the easiest way to kind of convert it into a number is to assume that you have 100 of it, right? And when you assume you have 100 of it, what it does basically is keep the number the same. So if you got 80% on your exam, you probably got 80 points out of 100, right? So that's an easy way to kind of convert it into the thing. I know I was going to go 20% on the exam, but it seemed not very encouraging. All right, so hopefully you didn't get that one. But a lot of times, for example, if we had something say like 4.25% by mass, so this is what is known as mass to mass percent, say calcium chloride. And if I wanted to kind of turn that into a usable sort of unit or conversion factor, basically what that would mean is I have something like 4.25 grams of calcium chloride and 100 grams of solution. So assuming 100 is a very easy way to convert things into a usable conversion factor. Now you have something that you can put into your dimensional analysis sort of calculation and use it to convert whatever you may be looking at. You know, if you knew you had 500 grams of solution, you could figure out how much sodium chloride would be in there, right, by multiplying them and so forth. So with that being said, officially speaking, like I said, been talking about what we've been seeing and how we've been setting things up, or what I refer to as dimensional analysis. And that is basically what some people call sort of the unit conversion type of situation, where basically using different units and equalities as conversion factor, you go from one unit basically to the next. And again, as we've been talking about, it is always opposites, the way that you kind of set them up. So if the unit you need to get rid of is on the bottom, you should put the same unit on top. And if the unit you need to get rid of is on top, you should put the same unit on the bottom to get rid of it. So the general steps to doing dimensional analysis sort of problems is it's sometimes very helpful to write what is given to you in the problem. Write what you want to find. Think about the appropriate equalities that you would want to use. Think about and write the appropriate conversion factors. You want to set up the problem like we've kind of been doing in some of these here with the units and the conversion factors. And you want to solve the problem for full credit there and to the right number of sig figs and all that. For full credit on an exam or quiz, you really need to show the last 2 steps is really what you need to show. If it helps you to kind of do the rest of it, you can, but you don't necessarily have to. But definitely the last 2 steps do need to be shown if you want to get full credit on doing any type of problem. So let's take a look at a pretty straightforward example here, which is obviously how many pennies there are in $3. We have our equality, which is $1 100 pennies. And we have our 2 conversion factors that you could get from it. Once again, you would obviously not use both of them in the problem. You always want to start with what is given, which is $3 in this case. Once again, it is not written as a fraction, but it's assumed to be over 1, which means dollars are on the top in terms of the units. We then want to put dollars in the opposite location, which means we would want to use this conversion factor to do so. That would give us 100 pennies is $1. Dollars, once again, will cancel. We are multiplying across the top. And in this case, coming back and dividing by the bottom, although there's not much to divide by in this case. That's going to give us 300 pennies. Significant figure-wise, this would be an exact number. That means we should default back here, probably mostly counted number, but we'll go with 1 based off of that. 3 that is there, and that means 300, no decimal point would have one significant figure in this case. Any questions on that there? Yeah. Yeah, so mathematically here, anything that's on top, it's like fractions, right? If you're multiplying fractions, you multiply whatever's on top. So technically you would take 3 times 100 and you would come back and divide it by 1. But obviously divided by 1 is not going to do much. But you could have numbers on the bottom, real numbers outside of 1. I guess 1 is still a real number. But you would have a number that you wouldn't need to actually divide out to get the answer. Yeah. Yeah, I think so. The entire slide. Here? Yeah. Yep. All right, why don't you try one here? You head over to the local AM PM Thirst Oasis. You grab yourself a 32 fluid ounces of Diet Coke. How many gallons did you drink? All right, there's some equalities. There's the respected conversion factors that you might be able to use. So set this up using dimensional analysis, showing the conversion factors, the units. Find the answer to the right number of significant figures. So see what you come up with here. Okay, let's take a look. So again, here we're going to start with what was given to us, which is 32 fluid ounces. We want to basically end up at gallons. So my pathway here that I chose is to take fluid ounces to quarts and then use obviously quarts to jump over to gallons. So the first thing I want to do once again is look at this, and I see fluid ounces is essentially on top. So I do want to get rid of that. So I do need to go opposite and use the conversion factor that puts it in the opposite location. So that would put my 32 fluid ounces per 1 quart. If I did stop the calculation right at this point, right, the units that I am in are quarts and they are up on top, right? And that's really important because now we could clearly see they're up on top. And we do want to get rid of quarts to gallons. So to get rid of quarts that are on top, I need to put the quarts on the bottom, right? So the opposite location. That means I do need to use the conversion factor over here that will do that. That's going to go 4 quarts, 1 gallon. Quarts will cancel. The only unit left standing here up on top is gallons. Once again, math-wise, we're going to multiply whatever is on top. We're going to come back through and divide by whatever is on the bottom in this particular case. That means I'm going to take basically 32 times 1 and divide it by 32. By the way, I'm going to hit equals and divide it by 4 and hit equals. You get 0.25 gallons. Now, in terms of significant figures, that's an exact number. Not going to worry about it. That's an exact number. I'm not going to worry about it. This number here has 2 significant figures. That means my answer here should have 2 significant figures as well. The answer here is 0.25. It is not 1/4 because that makes me think you're lazy to divide out the number. Yeah. So do not leave an answer as a fraction. Not maybe for this particular case, but for this particular case. But I have had people write things like 333 miles over 855 hours. That's my answer. That gets a big X. Yes, so don't do that. Don't leave any answer as a fraction. Yeah, divide it out and get a number and the appropriate units. Any questions on that there? Now, for points on the exam, what you need to show, once again, without all my arrows and stuff here, you basically need to show this setup and you need to show the answer. So that's basically what you need to show. Once again, if all this stuff helps you, you could do it, but you don't necessarily have to show it. But you definitely have to show what's on the bottom there. Any questions on that there? All right. Let me try another one here. We got an antibiotic doses of 500 milligrams is what we're looking for. If the antibiotic is ordered as 250 milligrams per 5 milliliters, how many milliliters would that person be given? All right, so looking at this, from milligrams to milliliters, it's very common as well in problems that we aren't given really a conversion factor in words, and we could turn that into sort of a conversion factor. So 250 milligrams and 5 milliliters, we could use it like that. We could also flip it around and use it the opposite way with the milliliters up on top and the 250 milligrams on the bottom. So once again here, we will start with what was given to us, which is 500 milligrams. Using our opposites cancel approach, we then need milligrams to be on the bottom, which is essentially dividing. So we do actually need to use it in that form. That will give us 5 milliliters over 250 milligrams. Milligrams will cancel. Once again, here we're multiplying the 500 times 5, and we're dividing by the 250, and that is going to get us 10 milliliters in this case. Question on that there. So let's talk about sig figs and what we should be looking at. Should I look at this number? I should, and it has how many significant figures? 3. How about this conversion factor? Should I be looking at it? In this case, you should. This is one that's given to you in a problem. It's not always that exact sort of conversion. So in this case, these guys have 2 significant figures here. So you would probably end up with 2 significant figures based on those numbers that are in the actual problem. Any questions on that there? All right, try another one here. We got surgery, 5 pints of plasma. How many milliliters would that be? Some conversions and equalities. So again, set it up using dimensional analysis and see what you end up with. Yeah, so let's take a look. We want to go from pints to milliliters. So this pathway that I chose, we're going to go first pints to quarts. Once we have it in quarts, we can then take it to milliliters. So starting with what was given to us would be 5 pints. That pints is up on top. So to get rid of it, we want to go on the bottom, which means we do need to use this conversion factor here. 2 pints is 1 quart. Once again, if we did stop the calculation right at this point, our units of pints will cancel, we'll be left with quarts. So we're halfway there. We need to then take it from quarts to milliliters. Again, setting it up like this, which is how you should do it. We can clearly see that the quarts are up on top. So we know that to get rid of them, we're going to go opposite and throw down our conversion factor over here. That will work. Which will then give us 946 milliliters is 1 quart. Quarts here will cancel. Once again, we're going to multiply the top and divide the bottom. And in this case, we'll take 5 times 946 divided by 2, basically. This is about 2365 milliliters. Now, in terms of significant figures, should I look at this one? I should look at this one, right? That's a metric to English conversion, which has 3. This one I don't need to worry about, right? It's an exact number. And this one has 2, right? Which means my sig fig should end up at 2, which would give me something like 2400 milliliters. Or remember as well, you could, if you want to do a little scientific notation, do a little deal like that, right? So that's another option. Yeah. Yeah, so here's the deal. If it is a conversion factor that is a straight metric to metric conversion, like, grams to kilograms or something like that, that's considered an exact number. If it is a straight like English to English or US to US sort of conversion, like 12 inches of the foot, considered an exact now. It is only really when you cross over between like English units to metric units, like 946 milliliters. Milliliters is more of a metric unit, right? And quarts there is more of a US or English type unit. When you cross over between metric and US, you should look at the significant figures in that conversion factor. The other place where you would probably want to look at the significant figures in something that you might use as a conversion factor is one that maybe you get from the problem itself. Like we had a couple there earlier where it was like in the problem, it was like this many milliliters and this many grams, you know, it's just kind of like a specific thing for that particular problem. It's not really always exactly going to always be that conversion. That would be another place where you should look at those type of guys as conversion factor. Other questions? Okay. Now there are a couple of exceptions, obviously, to the metric US one. The two major ones is the 1 inch is 2.54 centimeters. That's why people always write exactly after that. So it's considered an exact conversion. And for our purposes here, they want you to use for the grams to pounds one, that 1 pound is 453.6 grams exactly. So they consider that more of an exact conversion. On the chart, as we saw earlier, there's like the 454 grams as a pound. If you would to use that as your conversion factor, technically it wouldn't be an exact conversion, and you should look at the 454 in terms of significant figures if you happen to use that. All right, let's try another one here. You are stranded 125 miles away from home, decide, hey, it's only 130 degrees outside. Let's take a walk. And you walk home at an average of 55 feet per minute, not stopping. Maybe. Okay, so let's take a look at this. So we got a couple things happening. We have a distance of 125 miles, or length. We also have this guy here, which is basically a rate, which is obviously how far you're walking per time, unit of time. And it's the rate that's really going to allow us to turn the distance into time, which is ultimately what we're looking for, because we're looking for how many days we need to get there. Now, we do have a problem because the length in miles and the length in feet are not the same unit, so you cannot use them together until you do some type of conversion. So you either got to convert the miles to feet or the feet to miles. It really doesn't matter. I'm personally going to convert the miles to feet. I then will use the rate to get to time and then go from minutes to days, basically. So I'm going to start with converting my miles into feet, and I'm going to use my first equality here to do so. I'm going to put the miles in the opposite location, which means 1 mile is 5,280 feet. The miles will cancel at this point. At this point, I am now in the units of feet. If you want to get an answer at this point, probably don't do so much rounding, right? But you get something like 660,000, I think. They do really want you to do these type of problems all in like one calculation. Personally, my preference, I don't really care if you do it in multiple steps or one giant calculation, but just so you know, as you go through your chemistry career here, they do want to kind of see it all kind of done in like one big sort of step. So personally, me, I don't really have that big of a preference if you do it in multiple steps or one big calculation, but you can. I'm going to use this as a conversion factor, which means I could also use it as minutes per feet. So since I did set it up like this, I could clearly see that feet are up on top, which means I actually need to use it like this, right? And that would be 55 feet on the bottom. So we will use our conversion factor that we got from the problem of 55 feet on the bottom per minute. At this point, the feet will cancel each other out. If I stop the calculation right at this point, I'm in units of minutes, which is close to what I want. I need to get my now self from minutes to days, yeah? And to do so, I know minutes are on top. So in a minute, in 60 minutes, there is 1 hour. That gets rid of the minutes, and now I am in hours, which is close to what I want. And as we talked about earlier, there are 24 hours that need to go on the bottom in 1 day. Hours cancel. Once again, here I'm going to multiply everything on top, come back and divide by what's on the bottom. 125 times 5,280 feet divided by 55 divided by 60 divided by 24. Going to give me 8.33 days. Yeah. Now, in terms of significant figures, don't have to worry about this one as that's an exact number. Don't have to worry about this one as it's an exact number. Should I worry about this one? I should, right? That's just from the problem. So that's got like 3 significant figures happening. I don't have to worry about that one since it's an exact number. I do need to worry about this one, which has 3 significant figures. So my answer should have 3 significant figures, like I got going on here. Also, a note about your calculator. When you do this, since we are essentially multiplying everything that's on top and we're coming back and dividing by what's on the bottom, people oftentimes will screw this up because they want to put all that into their calculator at once, and they do not know how to properly do that with parentheses and stuff like that. So again, if you want to make sure that you get the right answer all the time, you could probably do this. This is almost a foolproof way. You can multiply as many numbers as you want on top. When you get to the very end here at top, hit the equal sign. Then I would divide it by the first number on the bottom, hit the equal sign. I would divide it by the second number on the bottom, hit the equal sign. I would divide it by the third number on the bottom and hit the equal sign. So if you kind of do it individually and type into your calculator individually, you will get the right answer all the time. If you try to punch it all in there at once, it is a very common, people come up with their calculator all the time and go, I didn't get that number. And it's because they try to punch everything in at once. Any questions on that there?